Okay, so by plotting this maximum response, we get the response spectrum. In this case, it is a displacement response spectrum. And if we plot these values on this tripartite plot, we get this tripartite plot from which all three, it's a special graph paper with four axes. On x-axis, we have natural period or natural frequency, either way. Y-axis, we have pseudo velocity, that is this maximum displacement, relative displacement multiplied by the natural frequency in radian per second, angular natural frequency. So that gives us velocity like quantity, and that is why it is called pseudo velocity. And if we multiply it by omega once again, omega n, we get pseudo acceleration. So that is acceleration like quantity. So for small damping ratio, pseudo acceleration and the total acceleration is the same, approximately equal. And in this intermediate frequency range, for small damping, the pseudo velocity and actual maximum relative velocity response is also approximately equal. So you can see that from this tripartite plot, we can have constant acceleration. If you see, if we take the average of similar spectra over this range, then these wiggles would be averaged out. We'll get something like a constant line parallel to the constant acceleration grid lines. Similarly, in this range, intermediate period range of intermediate frequency range, the constant velocity line would be parallel to this constant velocity uh, grid lines. And at the long period range, it is proportional to the displacement. So spectral displacement is some constant multiple times the peak ground displacement. So to say. So on this, so same, it is essentially the same quantity, but we can read different quantities at different period range depending on which one is more significant. So for short period range or high frequencies, acceleration is more significant. For long period range, displacement is more significant. At intermediate frequencies or periods, natural periods, velocity is more significant. And that's how this method of constructing design spectrum based on four periods. If you look at the USGS hazard map, they specify these contours of spectral acceleration at four periods. At short period range, that is around 0.2 second. At 1 second, that is constant velocity range. And at 5 second, that will be constant displacement range. And then with peak ground acceleration, ZPA. So with these 4 points, we can actually construct the entire design spectrum. So yeah, all these different periods calculations are not required. So with that, we complete our discussion on this dynamic response and characterization of the ground motion. Now let us move to the main topic, that is probabilistic seismic hazard assessment. So probabilistic seismic hazard assessment essentially uh, comprises, as I mentioned in the while comparison of the two zoning maps, it takes into account the seismicity activity, seismic activity of a region, and try to delineate, make a difference between which area is more active and which area is less active. So ideally, it is based on some kind of source zonation, seismic source identification, and then where some kind of characterization, the distribution of earthquake magnitude distribution, how the magnitude, different magnitudes are distributed. So these are all estimated from seismicity catalog of the region. And then from these, distance and the magnitude and distance, where for the site, how far it is from the location, so what is the distance measure. So because earthquake is an unknown quantity, so we generally assume earthquake can occur anywhere. So distance probability is uniform over certain range, the magnitude. That distribution depends on the seismicity catalog, past seismicity occurrence data. And then using this magnitude distance, we can use what we call as ground motion prediction equation to predict what is the ground motion. For example, peak ground acceleration or spectral acceleration at 0.2 second, 1 second, or 5 seconds, so on. So that can be predicted for different combination of magnitude and distance. And with this, we calculate what is the probability of occurrence. I mean, this is annual accidents probability. What is the annual rate of accidents of any ground motion parameter C above a certain threshold? And that is how we actually plot this kind of annual accidents curve, annual frequency of accidents. So this is essentially inverse of return period, because these values obviously are going to be very small, not so easy to remember. 475 here is easy to remember. So what we are computing here is 1 divided by 475. So annual frequency of occurrence, reciprocal of that will be 475. So 1 over 475, we pick from here and then go horizontally and then work out our way, which way it is going to be. And that is how this is uniform hazard spectra are actually worked out. Right, so the critical motion, I mean, all this comes from the data. The only thing here is, in order to use this uh, statistics, we need to identify, we need to take into account that Poisson process model is used in these definitions, the 10% probability in 50 years. That is based on Poisson process model of earthquake occurrence, which is based on essentially independent event occurrence. There is no relationship. I mean, the events are completely random in space and time. Now, we know from basic physics of the problem that every large earthquake is preceded by a few foreshocks, and aftershocks continue after a long time. So these are not really independent events. So this is what we call as when a large earthquake will always occur in a cluster. So in order to make this data suitable for Poisson analysis, Poisson process modeling, we use what we call as a declustering process. Now it is not an exact science because we don't know how the aftershocks are to be distinguished from the main shock. To make it a point, particular Gorkha earthquake, 2015 Gorkha earthquake, two magnitude 7 events occurred on the same fault within a span of 1 month. Right? Now, which one is a foreshock, which one is an aftershock, which one will be considered in hazard analysis, which one will be discarded in hazard analysis, or do we consider all of them, and what happens to the smaller events in between? Are they foreshock, aftershock, or what? So there is a lot of subjectivity involved, and there are different algorithms, this clustering algorithm. All of them provide different results. And after applying declustering algorithm, what we obtain is this seismicity rate of the region. Now, obviously, this depends on which declustering algorithm are we using. And as I said, there is no exact science behind it. Different declustering algorithms give you different values of seismicity rate, and this seismicity rate critically influences this entire calculation. Now, in addition to this seismicity rate, the another important factor is this ground motion prediction equation. Now, what is this ground motion prediction equation? Just to explain this idea, so these are the ground motion. For example, this is P ground acceleration. So collect a database, acceleration database that I showed a collection of time histories of different earthquakes. So we just plot magnitude P ground acceleration in this range. So this is, we'll see, I mean, naturally, this is a random event, so we lot of scatter here, right? And then this data will obviously have some median value, there will be some scatter around it, so some standard deviation. So this is median value, this is 1 sigma, median plus 1 sigma, this is median minus 1 sigma, this is median minus 2 sigma, and this is median plus 1 sigma. So as you can see this, as we encounter and enclose larger and larger bounds, data begins to be contained within those bounds. Right? So the problem is this scatter. So when and this, how do we model? Do we really need to model this scatter? That is the problem. So let us go ahead. So this is more broad idea of the probabilistic seismic hazard assessment, source zone characterization. Using seismicity catalog, we find out what is the distribution, how the magnitudes, earthquake distribution, and then for the magnitude distance pair, what is the ground motion prediction equation based on the available seismotectonic model and site conditions. And for each of the source zones, we find out what is the seismicity rate and then compute what is the probability of exceeding particular ground motion threshold. So different ground motion thresholds, you have these different curves, annual exceedance frequency curves, and just work out what is the desired value corresponding to desired return period that you want. So now look at where does this ground motion prediction equation come from. I just talked about the subjectivity in the seismicity rate. Now we will focus on this ground motion prediction model. Right? Now a common representation is general form of ground motion prediction equation combines several effects. So there is a magnitude dependence. So y is the ground motion parameter. It could be ground acceleration. It could be spectral acceleration at 0.2 second, spectral acceleration at 1 second, or spectral acceleration at 5 seconds. Right? So some magnitude dependent term, some factor function as a function of source to site distance, and then there is a combined effect of magnitude and distance together, because these two are conflicting quantities. Magnitude increasing will generally increase the intensity, distance increasing will generally decrease the intensity. So there is a interplay between them. And then there are several factors about what kind of source it is. Is it a strike slip or a thrust fault, or is it a subduction zone, or whatever? And then there are random deviations, random effects, epsilon. So epsilon is a random variable representing uncertainty in y, essentially to model this scatter in the data. Right? So this is a product model. Each effect is assumed to have this multiplier effect, and naturally this is multiplier effect. So if I take the logarithm, all of them very conveniently break into individual summations. Right? And because of this, once I use this logarithm, then very interesting thing happens. All of them are individual, and then this immediately opens up the range, because by definition, when we plot these values, these are by definition only positive. So obviously, normal distribution doesn't work. Right? So it has to be one-sided distribution. So which one-sided distribution can we do? Normal distribution is very well understood. We are very comfortable with normal distribution. So our first attempt is always to convert everything into a normal distribution some way or the other. So once we take this positive value, once we take the logarithm, we open the range. Now this logarithm of this positive value can be both positive and negative, and immediately the possibility of fitting a normal distribution opens up. And that's how it works. And usually assumed to be log normally distributed due to multiplicative nature of the terms in ground motion model. and which reduce to a simple summation of logarithmic terms. Right? Now, this is an assumption. How good that assumption is something that we need to look at because it will have some serious implications. So, I was talking about positive values, distribution for positive values. So, these are called skewed probability distribution, which admit values, variable admitting values only in one side of the axis, so only positive values. So, there are three skewed distribution which are commonly used. Uh, Three of them are Weibull, log normal, and gamma. So just a case to emphasize the difference in this distribution. So this is some empirical data, and as you can see, all these three data, all the three distribution will describe this data reasonably well. From hypothesis testing, none of these distribution can actually be rejected, most likely, right? And the problem is when we have this empirical data, all this data that we have gathered is actually observed data, isn't it? At naturally occurring earthquakes, that data we are looking at. Now, obviously, data we will generate will come from most probable value region, so where the values are most probable. And here, there is really no difference between different probability models. So all of them can be made to match each other with suitable choice of parameters. The difference is really in the tails. And as you can see, the difference in the tails is what you see here, QQ plot. Towards the higher quantile, log normal distribution is way far away from the actual trend, actual data. Right? So that is a fact tail distribution. Now the problem is we are never going to have data in this range. Tail region, very low probability event, nothing comes in this. We may have to wait for maybe thousands of years to get sufficient data to have some good idea about these tails. But we can do simulation, we can run simulations, and even with large number simulations, uh, I can say that this log normal doesn't really fit the data uh, towards in the tail region, right? So just to drive home the point, all three distributions, namely Weibull, log normal, and gamma, can describe the underlying data represented by this histogram. Log normal distribution significantly deviates from the data trend in upper quantile. So that is something that we should keep in mind, that log normal is a heavy tail distribution, large probability mass in the tail region about which we have no reliability at all. Now comes the problem that I was referring to. Here you saw the probability calculation was just summation and two integrals with respect to the magnitude and distance, right? And summed over all source zones. So that is what gives you this. So essentially this was used for median value and median curve of the ground motion prediction for given scenario model of magnitude and distance, and that is how it was being worked out, and that is how Alger, Mason and Perkin originally computed the 475-year return period MAC, and that was adopted by ATC 306 committee. Now mathematicians take over now because now we are assuming it log normal, and log normal has a standard deviation, and the variation in the data also should be accounted for. So we need to integrate the contributions from all this data, the entire probability model across the whole data. Now this is where the Stone Canyon earthquake 1972 example comes into picture, right? That data would be somewhere here, let's say, right? Very far away. Now, if I want to include that data in here, because this data is deviating, it has already pushed the median little higher, right? Because of this large value here. And then if I try to include that in our calculation, that range in the calculation, I am effectively considering, because this is log normal is an open-ended distribution. So even a small magnitude earthquake, which is not damaging at all, will have some finite probability of exceeding certain ground motion threshold, and it will contribute. Right? So this value actually depends on how much epsilon I account for in this integral. So one more integral is added with respect to the residual, and that is what the mathematical interpretation of PSHA is. Once you assume this log normal, then one must integrate across the log normal distribution of ground motion residuals to correctly calculate exceedance rate. Now this correctly is in mathematical sense. It has no correlation with the actual physics of the problem. Right? They are just being so. Engineering is left aside, mathematics takes over without any physical basis, as I will show in subsequent terms. So this is same probability. FMR is the joint probability density function of magnitude and distance. Fe is the probability that ground motion deviates epsilon times standard deviation from its median value, and this I is an indicator function which is equal to 1. As I said, some magnitude distance combination for some epsilon will always cross the chosen threshold, and if that happens, this takes value 1, otherwise it is 0. So effectively, all magnitude distance combination for some epsilon will contribute. But so far, so mathematically perfectly fine. But is it really valid? Use of log normal distribution for residual is a matter of convenience, because we just assumed this positive value, we don't know how to model it, take the log, very convenient, theoretical limit lifted, the values are ranging from negative to positive, so normal distribution to this range is possible, so we assume log normal. Normal distribution is very stable and convenient distribution. All sorts of probability plots are available. Right? But this log normal distribution for residuals is a matter of convenience without any concrete evidence. First time this use of log normal distribution was suggested was in 1970 by Louis Esteva. In this collection of articles edited by R.J. Hansen in this book brought out by MIT Press, Seismic Design for Nuclear Power Plants. And there he writes, distributions composed of segments of the log normal family were adjusted to each set of data in order to facilitate further computation. He never claimed entire data range to be modeled by a single log normal distribution. He fitted one log normal for this range. He fitted another log normal distribution for this range. Please note the change in slope here. So change in slope on this probability paper indicates difference in distribution parameters. So I don't really know how many people who use log normal distribution have actually and refer to this paper have actually read this paper, because Louis Esteva never claimed that log normal distribution is applicable over the entire data range. He only taught that it is a convenient thing that you can use some log normal parameter in this range, some log normal parameter in this range, some log normal parameter in this range. If I were to look at this data, I would probably split it into two parts. It seems much better fit. One part here, and another part here. Right? So it's again, there is no science here. It's all assumed values, some convenience. But convenience that is not examined because it hides early truth that we don't really know what is happening here. So nobody talks about it. Everybody now uses this log normal. It opens up the entire possibility, and that happens. Now, what are the consequences? The first effect of this came with the seismic hazard assessment of Yucca Mountain region in Nevada. Yucca Mountain region, that is where the nuclear waste repository uh, was being constructed. They were looking at the problem, what is the ground motion earthquake occurrence for very low probability of accidents, because to avoid the nuclear containment effect, nuclear radiation leaking out. So, if we do not truncate the log normal distribution, no truncation, we just allow it to go over whatever value it wants to be calculated, then it turned out that for Yucca Mountain region, for annual probability of accidents of 10 raised to the power 7, P ground acceleration turned out to be 10 g. 10 times acceleration due to gravity. Design earthquake ground acceleration, peak ground acceleration. Obviously, that is impossible. Because log normal distribution is a mathematical model, it has no constraint coming from uh, physical limits. The energy release is finite, material strength to accommodate that much strain is also finite. It cannot accommodate infinite strain, so it will rupture much before energy corresponding to this kind of ground acceleration can ever be accumulated. So then some effects were studied because this problem was a serious problem, and then people started looking at how do we define. Now, obviously, open-ended is not possible, so we need to put a upper bound on this integral with respect to epsilon. How should we put an upper bound? Right? So people try to work out different values. So again, what Algermison-Perkin did in 1976 was based on these median values. Now, if you integrate with respect to epsilon and truncate that integral at 1 epsilon, this is what you get in low seismicity region. The difference from median keeps on increasing as your annual frequency of accidents decreases or return period increases. So with 2 epsilon, this is what it is, 3 epsilon, 4 epsilon, so on. And this is for low seismicity region, they assume. So Baumar et al. Worked out some hypothetical parameters, hypothetical sites with low seismicity. As you can see, for 475 year, this is the top of the line that you can think of, corresponds to 475 year return period. So really no difference. Right? Whether you take 1 epsilon, 2 epsilon, 3 epsilon, really no difference. Right? Even median value gives you the same number. And this is what Algermison-Perkin computed. For high seismicity region, the median value is what Algermison-Perkin computed. For high seismicity region, the effect of epsilon is much more pronounced. Even for 475 year return period, the difference between median and 2 epsilon is about a factor of 2. So median value is somewhere here, 2 epsilon is somewhere here, right? And then 3 epsilon, 4 epsilon subsequently do not make that much significance at this level, but difference becomes much more prominent if the return period increases. For example, 2475 is somewhere here. So even median value is somewhere here, 1 sigma, 1 epsilon is equal to 1 is here, epsilon is equal to 3, 2 is here, 3 is here. So now all of them will get, if I don't specify what truncation level I am using for this probability calculation, all of them correspond to the same return period, right? And that is my biggest question with this revision. Nowhere in the code it is mentioned what epsilon value has been used to truncate this probability integral. From the values that they have quoted, it appears that it is at epsilon is equal to 3. So this is the curve that they are following. And the difference that you see in the high seismicity region, in high seismic zones, the difference of 85% or even 100% if I increase the occupancy to 200 is because of this epsilon, large epsilon value being used. And this is again sensitive to seismicity rate that I mentioned, right? This, if this rate is estimated to be large, again the probability calculations are going to be much larger. Evaluation numbers are going to be much higher, right? So again, there is no justification. Which algorithm is a rational algorithm? There is, it is all kind of data fitting exercise. Some earthquake happens, some kind of data suits Poisson distribution model. They recommend, it is recommended to be used, and that same model fails in some other earthquake. Right? So not really very scientific way of declustering. So how to compute this seismicity rate? Nobody knows what is the exact seismicity rate. If you really want that 10% probability in 50-year designation, otherwise you don't really know what probability you're talking about. So effectively, 475-year return period can be this value, it can be this value, it can be this value, or it can be this value, depending on at what limit I am truncating that probability integral, right? For the same seismicity rate, which is again contingent upon the choice of declustering algorithm. So none of these details are available. So you choose different parameters, you may come up with very different values for the same 475 year, 975 year, 2475 year return period events, right? And nobody can challenge because my judgment, my assumption is as good or as bad as anybody else's assumption, right? So the problem here is, again, why do Yucca Mountain and extreme ground motions at that region, at that site? Basic element of any PSHA calculation is that any one earthquake has a certain probability of occurring, and that once it does occur, some ground motion level has a certain probability of being exceeded. Given the magnitude and distance of that earthquake, the probability of exceeding that ground motion for this single earthquake is the product of earthquake probability and its ground motion probability, generally expressed as a per annum basis. Customarily, the probabilistic seismic hazard assessment involves summing the contribution of all such earthquakes at all magnitudes and at all distances, calculated at whatever range of ground motions or hazard levels is of interest to the analyst or client. Right? So it all depends on what epsilon value do I choose. And different epsilon values will give very different values if the region is seismically active. So now, this is all mathematical. So once this problem was detected, Yucca Mountain, it is in Nevada state. So two professors, James Brune and John Anderson from University of Nevada, Reno, they started uh, looking at this problem. I mean, these kind of ground motion are not really practical. And is there any evidence of such extreme ground motions having ever occurred in the historical times? And when they started looking for, they came across such kind of very what they called as precariously balanced rocks. So if you can see that this is a very a delicately poised rock mass which can be toppled even by a simple push of hand. Right? And you can work out the what is the force required and divide by the mass of this block, and you can work out what is the equivalent horizontal acceleration that will be required to topple this based on the geometry and centroid, and it works out to be some value. I'll come to that. But they did lots of investigation. They dated these rock masses wherever they cited them, and they were known to be, they were established, their age was established to be exceeding 10 kilo annum, so 10,000 years. They were at least 10,000 years old formation. Right? Now, the PSHA, probabilistic seismic hazard assessment estimates at these sites were found to be much, much larger than the acceleration that would have toppled them, which could have toppled such formations. Right? So that's a physical problem. The PSHA, the completely mathematical undertaking of integrating over the residual epsilon, is completely devoid of any physical explanation, physical constraint. There is no physics based constraint on that. Right? So they worked out that this particular rock mass will be toppled at acceleration of 0.36 g, right? And that was for static push. So in accounting for the dynamic effects, 33% increased, it works out to about 0.47 g. And they confirmed this through number of shake table experiments. They simulated a similar rock mass and then they tested it on shake table at what acceleration will it topple. And they found that it is about 30% higher than what is worked out using static push test. Right? Now that 0.47 G level is here, right? And for 10,000 year age of that rock mass, that is the minimum age, at least 10,000 year old. So there is a factor of, I mean, the time span here. So this block should have toppled 10 times over in the period since it was standing. Right? So this is the 10,000 year return period ground motion level. Right? So it should have been toppled 10 times over. The 0.47 is somewhere here. So about 10 to the power 3, 10 to the power minus 3, 9.5 times 10 to the power minus 4. So almost 10 to the power minus 3. And 10 to the power minus 4 value is somewhere here. So it should have toppled about 10 times over during this its life on Earth, right? So that's a serious problem. Inconsistency with the physics of the, I mean, what is the evidence on ground? And then they looked at, plotted these black diamonds are similar precariously balanced rocks, and they found that plotted these on the uh, 2008 PSHA based seismic hazard map of USGS. They found that, I mean, most of these rocks are intact, and the ground motion predicted, P ground acceleration predicted by, I mean, used by the, recommended by USGS seismic hazard map were much, much larger than the values which would have toppled all these precariously balanced rocks in this region. This is where that entire San Andreas fault region, right? So these precariously balanced rocks have been exposed for greater than 10,000 years without significant shape alteration. And these precariously balanced rocks, as currently situated, have survived the set of ground motions that have occurred at their location since the end of last glacial periods. And so much so that the hazard from the median of ground motion prediction equations without accounting for the scatter, even the median values are too high at certain PBR sites. And those are because the median itself is shifted up because of those outliers, which are outliers, stray points which have no damage potential. And that comes into, we'll look at that. I mean, this also was studied, damage potential. So these data points, they were from this ground motion prediction equation, particularly uh, one particular ground motion prediction, this Abramson, was used, and this is the median trend and this is the scatter, and then they divided the line epsilon. Median is of course truncation level, epsilon is 0, then epsilon is equal to 1, epsilon is equal to 2, epsilon is equal to 3. Right? Now they also did one interesting thing. They looked at, they picked up this data, picked up the time history corresponding to these data points, and found out, computed their damage potential of the ground motion. There are several ways in which damage potential structure can potentially be damaged due to this ground motion, how likely it is. So that is what we call as damage potential. There are several measures of that. So they did that analysis. So what they found, I mean, in this plot, right side, you will find that this is, the dotted line separates the non-damaging motions from potentially damaging motions. And all these high residual events, high residual data points, they fall in this non-damaging region. Please correlate this with my earlier comment about Stone Canyon earthquake event. This is high epsilon point, very high PGA, but this time history itself has no damage potential, very, very weak motion, cannot damage any structure. Right? So this is what is coming from high epsilon points. And that is what the whole point is with this probabilistic seismic hazard assessment, that unless we are careful about the legitimacy of integral over residual, large residual values, we are really not doing justice to the profession. Those are not, we are taxing, unnecessarily increasing the seismic hazard purely on the mathematical basis, which has no physics based relation to the damage potential of the motion. These are just outliers. We should just stop them. So typically from this study, we should not integrate. I mean, we should, ideally we should just be talking about median, but if you want to be more prudent, more safety conscious, maybe we can just take 1 epsilon. That is what it will cover this data, and rest of them are very low probability event. I mean, the safety margin in our design codes is essentially designed to cover against these load factors. We underestimate the strength, we overestimate the load effects, and so on. So those will take care of these occasional very low probability happenings, considering the risk that is acceptable in our society. Right? So to emphasize, high residuals mostly correspond to the non-damaging ground motions. Now, this precariously balanced rocks, or more formal term is fragile geological structures constraint on probabilistic seismic hazard, was actually used on a existing structure, Clyde Dam in New Zealand. There is a fault very close to the Dunstan Dam, Clyde Dam, that's Dunstan Fault, and it has experienced two, this dam has survived two 7 plus magnitude events. And there are several precariously balanced rocks, 7 precariously balanced rocks, located about 2 kilometers from the dam and the local active Dunstan Fault. And all of these precariously balanced rocks are in the range of 24,000 years to 66,000 years. And those have survived at least two large 7 plus Dunstan fault earthquakes. So when they use probabilistic seismic hazard analysis and leading to PGA that would topple these precariously balanced rocks, those branches were eliminated. Then the mean 10,000 year return period spectrum for the hazard estimate is used as a safety evaluation earthquake, and that was evaluated to be 0.55 after removing these logic tree branches. And this is much reduced, almost by a factor of 2, compared to the value of 0.95, which is based on just blind application of PSHA, right, for the evaluation of safety evaluation earthquake. So that's a cautionary note, not to be taken away by these triple integrals and lose sight of the physics of the problem. Models are for our use. None of the mathematical models are correct. Let us understand that basic fact. All models are wrong, but some models are useful within certain range, certain framework. Right? Let us not extend the model to outside its domain of applicability. To bring home the point, the revised United States National Seismic Hazard Map of 2023. So this is 0.2 second spectral acceleration, right? And this is a relative map. I'm not plotting here, I'm not showing here absolute values. This only shows the difference ratio of 2023 values with respect to the previous map of 2018 National Seismic Hazard Map. And this blue line, dark blue, corresponds to reduction in amplitudes, spectral acceleration at 0.2 second by a factor of 3. So this violet color, so dark violet region. So in all this region, the spectral acceleration has decreased massively. This is the Seattle area, the subduction zone, very active subduction zone. This is now San Andreas fault zone. So everywhere you see, there is a massive reduction in seismic hazard estimate. Wherever you see this increase, this is in low seismicity area where a smooth graded seismicity model is adopted. So let us, that is not the point of discussion at the moment here. So in the seismically active region, you will find that the hazard has considerably reduced as much as by a factor of 3 here. And in computing this, they have not used any kind of declustering. They just used whatever data was available, calculate the seismicity rate from that, and then they did not use any integration with respect to epsilon. Right? They just used three values in logic tree, weighted sum. Most of the weight was given to the median value, then equal weight was given to median minus 1 sigma, median plus 1 sigma. So essentially it is works out to more or less same value as the median value. And that is how this value has come about. This map has come about, and that median value estimate itself was used by original prescription by Algermison and Perkins. So to conclude, the implications of these revised seismic hazard estimates using return periods of United States hazard maps for Indian context is not justified without any basis, without explaining why that should be relevant for Indian context to define the minimum seismic load in view of the vast differences in the risk behavior and the cost of living and cost of everything. Although it is not mentioned anywhere in the code, it appears that the truncation level of epsilon is equal to 3 has been used to truncate the log normal distribution for integration across epsilon in the computation of annual accidence rates. So this is, I would say, concealing the crucial information, because without this, the results are not repeatable. And this has been, I would say, the greatest disservice to the profession by the MAPS subcommittee of CED 39. Validity of log normal distribution at high epsilon is questionable, right? So beyond 2 epsilon, there is really no data, no basis why log normal should be continued beyond epsilon value of 2. And moreover, such high epsilon values are primarily contributed by the ground motions of minimal damage potential. So those high epsilon values are anyway irrelevant as far as the structural response to the ground motion is concerned. Those are outliers. They should be treated as such. Seismicity rate epsilon and the truncation level, seismicity rate nu and the truncation level epsilon significantly affect the computed hazard, especially in the high seismicity region, and that is why we are getting the difference of 85% in these two versions, despite the attempt to match the seismicity in the low seismicity region, lower zones. And finally, to conclude, the recommended seismic hazard estimates in the 2025 revision result from an unvalidated mathematical model with dubious assumptions. So all doom, are we doomed? So I don't want to end with a very gloomy conclusion. As I said, the road to performance-based design, improved seismic performance is the drift control, and for that, we in the Department of Earthquake Engineering have been developing several technologies for drift control, and you can have a look at these uh, couple of videos that you can find on this links. Uh, this is the linked uh, concrete blocks, slotted concrete blocks with viscoelastic link elements that can be used to construct, just assemble the buildings with like a Lego toy structure. And you can witness the test in this link. And we exhausted the test capacity. We exhausted the limits of our test facility. We could not damage this model. Right. So that's a very, very heartening fact that these kind of blocks can be prepared and then just interlinked together at site, and the entire building can be constructed in one day, no issues. And then second one, this one is a distributed friction tuned mass damper. Uh, Very conveniently, it can be distributed over one floor. It can be distributed across several different floors, across height also, and with the effect that we can control, we can reduce the seismic earthquake drift in the buildings, in the structures by as much as 50%. And this is very critical. Drift control is very, very critical, particularly in buildings on hill slopes, where because of short column, those are very, very vulnerable to earthquakes induced drift. So these tune mass damper, distributed tune mass dampers can be very effective measure to protect those kind of buildings. And there are more such technologies that are being developed, that are uh, patents are filed, publications are in pipeline, and you can refer to those as they come up. So to conclude, it is possible to achieve no damage or minimal damage performance objective even for the rare and severe ground motions, no matter whatever ground motion is specified by the MAPS committee. Even 1G ground acceleration, peak ground acceleration event can be handled very easily. And these provide promising solutions for improving the seismic performance of irregular and seismically deficient buildings. So that's all I have to say. I look forward to receiving your views and questions or discussions. Thank you.